So, last time, what we did was is that we talked a little bit about uh, entropy, right? Uh, Closed system entropy specifically. We did a question. We did not do this one. We did the one before it, which was here. This right here. And what we're going to be doing today is we are going to be doing, we're talking about directionality of process. Mr. Michael, you got something for us? Wait, yeah, I did start it. So, um, as I said, we're trying doing directionality of process. So it says, our study of the second law of thermodynamics, which is what we've been doing for quite a while, uh, began in section 5.1 with the discussion of the directionality of processes. In this section, we consider two related aspects for which there are significant applications: the increase in entropy principle and a statistical interpretation of entropy. So, like I said, this might be a shorter section, but we're going to do some questions afterward. So it says, the increase of entropy principle. So it says, in the present discussion, we use the closed system energy and entropy balances to introduce the increase of entropy principle. Discussion enters on an enlarged system consisting of a system and that portion of the surroundings affected by the system as it undergoes a process. Since all energy and mass transfers taking place are included within the boundary of the enlarged system is an isolated system. And it says an energy balance for the isolated system refers to this. So it's delta E of an isolated system is equal to 0, right? Because essentially what they are saying is that all of our energy transfers, our heat, our work, anything that takes place in here is being accounted for, right? So essentially nothing is leaving. So that means the delta energy of the system has to be equal to 0, right? There's no change in it because everything is included under the umbrella, right? And then it says, because no energy transfers take place across the boundary, so nothing is leaving. How about that? Easier definition. Nothing is leaving. All things are happening internally, okay? Then it says, thus, the energy of the isolated system remains constant. Since energy is an extensive property, its value for the isolated system is the sum of its values for the system and the surroundings, respectively. So equation 629 can be rewritten. So delta E of the system plus delta E of the surroundings is the same thing as delta E of the isolated system. And it's all equal to 0. It says, in either of these forms, the conservation of energy principle places a constraint on the processes that can occur. For a process to take place, it is necessary for the energy of that system plus the surroundings to remain constant. However, not all processes for which this constraint is satisfied can actually occur. Processes also must satisfy the second law, as discussed next. So right here it says an entropy balance for the isolated system reduces to this. So delta S of an isolated system has to be equal to, once again, remember this equation, it is the integral of Q over T of the boundary from states 1 to 2 plus the entropy produced by the system, right? So, but if you recall, because our system is isolated, it means nothing is leaving, which means that Q goes away, right? Because nothing has actually left. So when Q goes away, that means that delta S of the isolated system must be equal to the entropy produced, right? It's sort of like that example we did the other day, I think 2 classes ago, where at the end we found that S2 minus S1, or delta S, was just equal to the entropy produced, right? Because there was no heat transfer. It was not rigid. I guess not. What was I trying to say? It's not. It was a heavily insulated. How about that? Heavily insulated system. So we said no heat transfer was able to leave. So therefore, it was just equal to the entropy change was only defined by how much entropy was produced during the process in between. Alright, so right here, it says where sigma isol is the amount of entropy produced within the system and its surroundings. Since entropy is produced in all actual processes, the only processes that can occur are those for which entropy of the isolated system increases. This is known as the increase of entropy principle. The increase of entropy principle is sometimes considered an alternative statement of the second law. Since entropy is an extensive property, its value for the isolated system is the sum of its values for the system and the surroundings, respectively. So equation 630a can be rewritten as the following. So what they did was they said delta S of the system plus delta S of the surroundings is equal to just the entropy produced. And it has to be, right? And then it says, notice that this equation does not require the entropy change to be positive for both the system and the surroundings, but only that the sum of the changes is positive. In either of these forms, the the increase of entropy principle dictates the direction in which any process can proceed. Processes occur only in such a direction that the total entropy of the system plus the surroundings increases. So what they are saying is this, is that inside of our system here, right, this box, oddly shaped box, because there is no heat transfer that is like bringing entropy in or removing entropy, right? Because remember, entropy is accompanied by heat transfer, right? Entropy addition or subtraction. What they are saying is the following: because this right here in any actual processes must be a positive number, right? Because this number must be positive, and what I mean is in real processes. It can be 0 as well, but that's for a fake process. Nothing is 100%, nothing's isentropic in that way. So it's never going to, there will always be entropy produced. So because that sigma must always be positive, that means this right here has to be as well. Because essentially what this is, it's the sum of the system plus the delta S of the surroundings has to be equal to the entropy produced, right? And if this entropy produced must always be positive, that means that this has to be positive as well. Does that make sense? Yeah, this quantity has to be positive. But these right here, one of these can be negative, right? And they will be. Just this sum has to be positive because it's equal to a positive number. You can't have a negative, like, let's say this is negative 10, and this is, 10 over here, or, 10 over here, positive 10. That means that one of them is going to be negative, and if you flipped it around, you would get a negative number, so you just can't. It doesn't work like that. Have to be equal to each other. Negative 10 is not equal to positive 10. So, it says, we observed previously the tendency of systems left to themselves to undergo processes until a condition of equilibrium is stated or attained. The increase of entropy principle suggests that the entropy of an isolated system increases as the state of equilibrium is approached, with the equilibrium state being attained when the entropy reaches a maximum. This interpretation is considered again in section 14, which we will never get to, chapter 14. It's not, I don't think it's covered in any class that we do. I could be wrong though. I just don't remember. And it says, which deals with equilibrium criteria. Example 6.5 illustrates the increase of entropy principle. Let me see, what is chapter this? What is this chapter? I'm looking at it just as a weird... Let me see if I'm... Sorry, I'm just actually curious. I think we actually did... Oh yeah, it's I think it has to do with Gibbs free energy. Okay, so I guess we do talk about it a little bit. Never mind. In later books, or in later classes. I think Thermo 3 is when you will do it. Okay. So, right here is a question, right? So this one is very similar to those other questions that we did, which is like the T final. So it's a, remember these type of question where it's a metal bar sitting in water. Find the equilibrium temperature, right? That's what this question is. So it's an expansion of that. So first, you have to find the equilibrium temperature of the metal bar and the water, and then the amount of entropy produced. So essentially, it's very similar. The process is the same as the one before, which is you find the equilibrium temperature, and then you have to find the amount of entropy produced. So that would be a little bit different. So we can do this one. Actually, we can just talk through it real fast. I don't really want to do this one. I want to do a different one. So we'll walk through it very slowly. So essentially what they're saying is that the final equilibrium temperature can be evaluated by an energy balance. So obviously in this type of system where it's just a bar and some water, kinetic and potential obviously go. Because it is contained within here, we're going to get rid of Q as well. We're saying that nothing leaves, right? This is an isolated system. We're giving an example of that here. And there's no work, which means that here, essentially the change of energy of the water has to equal the change of energy to the metal, right? And so this is by, you can think of this by inspection, right? If this bar is, as it says, 1900 degrees, it has a certain energy level, right? It's very hot. The water is basically room temperature water, right? So essentially, this water, any energy loss from this bar is going to go to the water, right? Until it reaches some equilibrium temperature. So they have to be equal to each other, right? The loss of energy of the metal has to be equal to the gain of energy of the water, right? It doesn't leave. We're just saying it doesn't leave because it's really well insulated. And then what they do is they set up the equation in that fashion. They say, all right, the mass of water times the CP of water times T final, the initial temperature of the water, has to be, when it's added to the mass of the metal and the CP of the metal times delta T, you end up with 0. And if you maneuver this around, you end up with this. Right? So what happened is essentially, because of how hot this metal was right here, it raised the temperature of water 5 degrees. Essentially, that's the final equilibrium temperature. The water went up 5 degrees, and the metal quenched down to 535 from 1900, which is quite a lot. And then it says the amount of entropy produced. So this is the part that we really wanted to get to. This first part was just kind of window dressing, right? We want to get to this one. So it says the amount of entropy production can be evaluated from an entropy balance. And so we're going to eliminate some things. It says since no heat transfer occurs between the isolated system and its surroundings, there is no accompanying entropy transfer. Ugh. So that means this part right here goes away because remember, as heat transfer comes into a system, Q on its coattails is also S, right? And if the opposite happens, there is obviously some removal of entropy, right? So they accompany each other. And so since it doesn't happen in this case, we get rid of it, which means that once again, delta S must be equal to just the sigma value, right? The entropy produced. So any entropy that we have in this system that is changed, it has to be accompanied by entropy produced. So think of it this way, is that to get to state 2's entropy, right, because this is S1 minus S2, which is an expansion of delta S, right here. To get to state 2's entropy, this has to be true. Essentially, the starting state's entropy, S1, has to be equal to S2 when you add sigma to it. Because any entropy produced plus the initial state gets us to the final state, right? So this is that logic, right? Anything we have added in between has to get us to the final state. Now let's look down here. It says, entropy is an extensive property, so its value for the isolated system is the sum of its values for the water and the metal, respectively, and the entropy balance becomes this. So we have broken this up into 2 parts. It is now delta S of the water plus delta S of the metal is equal to sigma. Okay? And now we move down here. Then it says, evaluating the entropy changes using equation 613 for incompressible substances, the foregoing equation can be written as this. So, I'm going to go back up really fast and find that equation. It's 613, they said, just to show you that we know where it is coming from. All the way back up. And we're almost there. So, right here. So this is what they've done. Essentially, they did delta S. So they did for the first one, they did delta S of the water was equal to this. And this is CP of the water, ln of T2 of the water minus or over T1 of the water. Now, if you recall, T2 will be the same for both of them because it's a final temperature. And then they subtracted, or they added. I think it was subtracted. They subtracted the delta S of the metal, which is the same equation. Okay, just to show you where all these things are coming from. Now let's. Oh well, overshot it. Who would have guessed that was going to happen? Anyone with eyes to see? Okay. Alright, where are we at? Oh, that's the gearbox. Alright, we're close. Nope. One more down. Okay. I should just remember what page I was on. Alright, so now here we go. We're back. So then what you do is you slide these numbers into here. So you have a mass given in the question, you have a CP given in the question, and all the other stuff, right? T final is the only thing you had to find. And then once you do that and you get all the units right, you will end up with sigma being this right here. So that was a question that, so essentially this is entropy produced by the process of the metal quenching in water. Being dropped into the water, I assume. Yeah. So that was the quenching entropy produced by the process of dropping it into water. All right. And now we move on to, I think we might talk very briefly about something like this. Although I don't think we're going to talk about this stuff over here. I might not actually. This stuff's things. It's a statistical understanding of entropy. There's actually a chapter on this, and we don't really get much into it. But I will read this section to help you maybe understand a little bit. So it says, building on the increase of entropy principle, in this section we introduce an interpretation of entropy from a microscopic perspective based on probability. In statistical thermodynamics, entropy is associated with the notion of microscopic disorder. From previous considerations, we know that in a spontaneous process of an isolated system, the system moves toward equilibrium and the entropy increases. From the microscopic viewpoint, this is equivalent to saying that an isolated system moves toward equilibrium. As an isolated system moves towards equilibrium, our knowledge of the condition of individual particles making up the system decreases, which corresponds to an increase in the microscopic disorder and related increase of entropy. So, I know that maybe that was a bit. Essentially, what they're saying is that as disorder increases, our knowledge of where these particles are at decreases. So think about it this way. Think about it as a beehive, right? I'm going to draw a beehive here, guys. This is going to be like a really bad one, but we're going to do a beehive. And it has like has a hole here or something. I don't know. This is going to be like a really dumb example. Alright, so there's the beehive, guys. So, inside of this beehive, this is pre-me kicking it. You probably have, if you had some sort of way of looking at it, you would know that there are some bees in here, right? And you'd have a good idea of where they're at, right? If I go up and kick the shit out of this thing, would you then have an idea, would you have less of an idea where they're at? Because they are now in what you would call disorder, right? They're in chaos. They're flying around the hive, getting ready to attack you. If the Bee Movie is anything to go by. I recommend that movie. It's pretty good. So, essentially what I'm saying is that it's once something happens, me kicking it in this example, this is me kicking it, something happens where all the things inside of it get a little wound up, and so we have less knowledge of their initial position or where they're at at any point. So that is the increase of disorder, increase of entropy, decrease of knowledge where they're at. Okay? That's a great example, by the way. Can I get a hand in the chat or anything? No? No applause? Anyway. It's pretty sad. Alright. So, it says, we use an elementary thought experiment to bring out some basic ideas needed to understand this view of entropy. Actual microscopic analysis of systems is far more complicated than the discussion given here, but the essential concepts are the same. Consider this right here, this figure. Consider n molecules, so some amount of molecules in here. initially contained in one half of the box over here, right? There's a partition, it's blocking them. The entire box is considered an isolated system. We assume that the ideal gas model applies. In the initial condition, the gas appears to be at equilibrium in terms of temperature, pressure, and other properties. So essentially contained within this, we have reached true level, true harmony, right? We are in here, everybody is good, right? We have a great understanding of what they are in here. And then it says, but on the microscope, so it says initial condition, blah, blah, blah. Let me see. Terms, temperature, pressure, and other properties. We know these things because they're at equilibrium. But it says on the microscopic level, the molecules are moving about randomly. We do know for sure, though, that initially all molecules are on the right side of the vessel. So we know they're all here, right? Because there's no way that they passed. So we know a little bit. We know that they are in here. We know they are moving randomly. And by the way, there are statistical models that can actually like predict these types of movements, but you don't talk about them in this class. That's kind of like five head level thinking, 5,000 IQ. But for here, we're just talking about a simple thought experiment. Then it says if we remove the partition and wait till equilibrium is reached again, as in the next figure, because the system is isolated, the internal energy does not change. Further, because the internal energy of the ideal gas depends on the temperature alone, the temperature is unchanged. Still, at the final state, a given molecule has twice the volume in which to move, right? So essentially, these molecules can move even further now. They were contained, now they are not. It says, just like a coin toss, the probability that the molecule is on one side or the other is now 1/2, which is the same as the volume ratio V1 over V2. In the final condition, we have less knowledge about where each molecule is than we did originally, right? You have half of a chance of being right. You see the point here? And it says we can evaluate the change in entropy for the process of figure 6.7 by applying equation 617 expressed in terms of volumes on a molar basis. The entropy change for the constant temperature process is this. So this was another equation previously done. They said it was 617. We won't go back and look at it, but this was it right here. This one had to do with volumes instead of pressures. And it says where N is the amount of the substance on a molar basis right here. Yeah, right here. That looked like an Ln though. It's divided by N. And then it says, next we consider how the entropy change would be evaluated from a microscopic point of view. So we're actually going to stop here about this because this stuff is, like I said, this is microthermodynamics essentially. It's like stuff that you do on probability of where things can be. We're not going to really go into that because there is a chapter on that. I think it's chapter, it might be 12. No, I don't remember where it is. I just know that it's in this book somewhere. But essentially, it is a chapter where you do a lot of things like this. But it might be 14. I don't know. But this is not something that we're ever going to do. And if you don't take the max level thermo at this school, you'll never do it either. So there's no reason to really deep dive into it. All the things that you need to know are as follows. Entropy comes in with or leaves with heat transfer. Entropy gain is from the process. And disorder is what we talk about when we talk about entropy, right? And the measurement of disorder is sort of based around what we know and what we could possibly know about the system at any given time. Think of the beehive and my great example that I think Michael was going to give me applause for, but then he stopped talking. I was pretty sad about that. So now, yeah, I kicked the beehive. I've never done that before. My brother had a big bee nest, like sitting like on his garage, and I think it was a wasp nest actually, and he had to shoot the little wasp spray from like 30 yards or something. Like he was just like he got one of those long guns of it because it was so big, and they were just buzzing around it. Yeah, he was really worried about that one. They were shooting it from so far away. They took it down though. Took down the Death Star with one shot right in the exhaust pipe. So, now, what we're going to do is we're going to do a question, And next time, we are going to start entropy balance for control volumes. So what that means is we are no longer on control or whatever closed systems. We're talking about entropy coming into systems as a rate of time, right? Okay? So that's what we do. And you notice how everything here has dots now. So, all right, now let me find us a good question here. That is not what we wanted. Let's see if this is a good one. I do want to make sure that I don't give us something really dumb. I don't like wasting your time that much. And you don't get paid by the hour. So, we will take a look here. Yeah, I thought the beehive was a good example. Although I bet you, like, if a thermo professor like was watching this, some guy's like, you know, really deep into it, he's probably like shaking his head, like, oh god, what a terrible example. Dr. Matthias would be very sad, probably. All right, so let me see if this is it. No, this is yeah, we're not gonna do that. We're not gonna do that example. It's really bad. At least in my opinion, it's not a very good question. I'll find something really quick here. I mean, honestly, I think we might. I don't know, because the thing is that so the questions in this chapter are all just like this one. For this section in the back of the book, they're all just like this. They are some compartment. Find the final temperature, find the final, you know, equilibrium, or that you find this stuff, right? You do this exact process. You find either the final pressure, you find the final temperature, and then you find the amount of entropy produced. Is there anybody in here that's like really, like they're not confident that they could do this process right here? Because it's the same question. It would just be doing this again, and I don't think that this was that difficult to begin with. But next time, we will do more. More questions based on like controls volumes. I might find one here, like your homework, before we start. Yeah, this is gonna be a really good one for the video. There's like just me droning on here. But let me get this. I'm gonna find one here. Find a question. And we are on homework 8 now, correct? Is that right? Nope, homework 9. Apologies. Let's find that. Let's find something like this. Yeah. I really want to find something that's like, you know, good, but I think I found one. I think we'll do this one. All right. So, develop a plot of the work done by the water in kilojoules versus the amount of entropy produced in See, I don't. Yeah, I guess that'll be okay. Whatever. We'll just do that. So I'm gonna do a notepad here, or not notepad, Paint. The world's foremost teaching tool. So, Paint, 5,000 pixels. And so what we're going to do is we are going to pull out a question right here. I'm going to read it to you, and then we're going to go over what each of those things actually meant, okay? So, now, first one here. It says, 2 pounds, or wait a minute. Oh yeah, okay. It says a piston cylinder assembly. So let's think about that. So I'm going to do given. And then we have piston cylinder. Okay, so that's one thing that we have, right? I'm going to turn the font down as well. I feel like that's kind of obnoxious. Okay. So piston cylinder assembly, got that one. And then it says initially contains a volume of 0.04 meters cubed. So we were given not a little volume. We were given a large volume. So this is total volume. So we have V1 is equal to 0.04 meters cubed. Okay. And it says we were also given that this is at 1 megapascal and 320 degrees C. So that's another thing. P1 is 1 megapascal, so 1.0 MPa. And we were given T1 is 320 C. Okay, so these are our initial conditions, right? And it's also water. So I'll put that up here, water. And then it says, the water expands adiabatically to a final pressure of 0.1 megapascal. So what that means is the following, is that whenever it says expands, and it says it expands adiabatically, what does this mean? Let's see how, as Michael said, the noobs in the chat get this one.
It's without heat.
Without heat, but what are we thinking about expand, though?
The second volume is greater than the first volume.
Yes, and what is... Yeah, the second volume is greater. That was what I was looking for. The pressure one was already known, but yes, that was exactly it. So we are saying P2 is going to be less than P1, clearly. We are going to say which is equal to, I guess, P2. I'll just put that there. P2 is equal to 0.1 MPa. And then we have this knowledge that V2 is going to be less than V1. So essentially what this stage is right here is it's sort of like the power stroke of a internal combustion engine for your car. It's like the power stroke, essentially. But obviously not with water. That'd be weird. But it's essentially...
It was compressing or expanding?
This is expanding.
So would the second volume be greater than the first volume?
Oh, did I write that wrong? V1 is this. Well, no, if it's expanding, that means the volume got bigger, right? Did I write it wrong? So V2 is less than V1?
Yeah.
Yeah, so I think it says this: a piston cylinder assembly initially contains that volume of water. The water expands adiabatically to a final pressure of 0.1 megapascals. So pressure dropped and volume increased. So yes, you are correct. I wrote it incorrectly. Thank you. So we got that. Now, it says to a final pressure, of that. And then it says develop a plot of the work done. We're not going to do that. We're just going to find the amount of entropy produced and the work done. That's what our goal is. So we know these things right here. This is what we got. Okay? This is all we got. So, does anybody have any ideas about how we might start something like this? Anybody? Let's go. We got 14 minutes to finish. Anybody know how we might do something like this? What is our first goal? As always, we have a goal at the start. We are being asked to find the work done and the entropy produced by the process. So I will put that up here. Thank you for asking. Find work of the, I guess not work cycle, work. Find entropy produced. Those are the two things. So we're trying to find entropy produced and the work. So okay, let's take a step back. We have two very clear states, right? We have state 1, which is defined by volume, pressure, and temperature. We know it's water. And then we have state 2, which is 0.1 megapascals, right? So, what should we do first? And this is basically the same thing for most questions, is that we should find everything we need to know about state 1, right? Is that fair to say? So let's start at state 1. That, like I said, no need to get too lost in the details yet. So state 1, we have pressure 1, we have temperature 1, so we can find everything we need to know about the other things, right? So let's go ahead and do that. So let's do this. Tables here. I have them over here. Trying to get things off my screen. I need another monitor, guys. Anybody want to chip in or no? So, right here. Let's go here. So we must go to the water tables, and we must go to make sure it's in the SI. So we are in the water tables right now. And we need to find out where it is. So I'm going to guess it's superheated, but we'll see if I'm right. So we said we're at 1 megapascal, which will be 10 bar, pretty sure. So 10 bar. And it says our temperature is 179.9. Are we higher than that? 320 degrees C, we are higher than that at 1 megapascal. So, which means we are superheated. Straight up, right away, superheated. So then we move over and find 1 megapascal, which should be 0.51 right here. So then we slide over. Let me pull up. Did I get rid of EpicPen? I think I did. Over here deleting things. So we take 1 megapascal and we slide over to our temperature, which is 320. So you go right here and you grab everything we need from here. Now, what are some things you think we'll need? Well, I can tell you we're probably going to need specific volume. So if it's a question asking about volume, always take a specific volume. If it's a closed system, we're taking U here. And we're also going to take entropy, because remember, we are going to need entropy later, because we're trying to find entropy produced later. So we're going to need 3 things here, in my opinion. Now, that's subject to me being wrong. We could need something else too, but I don't know that quite yet. So I'm going to go ahead and take these things from the table. So little v1 is equal to 0.2678. I'm going to say meters cubed per kilogram. And then we have U1 is equal to 2826.1. And then kilojoules per kilogram. And then the last one is entropy, which will be S1 is equal to 7.19. So 7.1962. And this will be kilojoules per kilogram Kelvin. So I'll just write this one out. I didn't want to write the other ones. It takes too much time, but we'll do this one. Okay. So we now have all the things that we wanted, right? We have volume, we have internal energy, and we have entropy of the first state. So we're doing good there. Now, we have that. Is there anything else that you think we need to know here? Or where do you think we go next? How about that? Anybody? Anybody know what we have to do here? So first, let's write out some equations here. And by the way, this question, because the way it's worded, we're plotting. The question's asking for a plot. We're actually going to only find equations for this. It's not going to be any actual answers unless we were given some value. So this is going to be a plot of work done if we knew something else. But we're going to find the final equation to plot these things. So what is the equation for this system then? Remember, it's a closed system, right? It's a piston and or it's a water in a piston cylinder. So what would be an equation for an energy balance? Does anybody have an idea?
If there's no heat transfer, you do the work that's I think going into this is going to equal the change in internal energy.
Yes. So you're saying that we're gonna, if we write this, we write Q minus W is equal to M U2 minus U1, right? Is that what you're saying?
Yeah.
Okay. So that would be our equation for this, because we're going to neglect potential and kinetic energy because they didn't give us any reason to find it. They didn't give us any heights or anything like that. Which obviously it's a piston cylinder, so there's not much I think there's pretty negligible anyway. But this is what we have now. As I think Tanner just said, is that one of these goes away because we have stated that there is no heat transfer because it expands adiabatically. So we are given that work is equal to, you could flip it around, but it's going to be U1 minus U2. So we're going to do that. So work is equal to M times U1 minus U2. And what I did there is I just took away the negative side and flipped the other one. Okay? So now, where are we running into problems at? Anybody? We do not know U2, correct. But let's expand some other things here. So the work is related to this stuff, right? So what about is there any way we can find U2? And by the way, like I said, this question is it's about cases. It's plotting. So we are picking values. But I'm going to give us a value to pick. How about that? I'm going to give us a value. So what I want is that let's say that let's say that S1 is equal to S2. Let's try that one. So let's say it's an isentropic process, right? Okay? So this was an S1 is equal to S2, and I know you guys are probably wondering, well then wait a minute, entropy produced won't be anything, right? Agreed. But let's say it's an isentropic process. So S1 is equal to S2. So what would we do now? So we would do S1 equal to S2, or S2. We're going to call this isentropic. So for this case, we would then take what? Tanner's got me the answer coming, maybe. Then we can find U2, correct. So the question initially doesn't give us any things. We had to pick them and insert numbers into there. That's why. But for me, I'm going to give you the only case that we're going to do. We're going to do where S1 equals S2 is isentropic, which means that we need to now go find stuff about state 2. And so let's write state 2 over here. So state 2. So what we know so far is that P2 is equal to 0.1 MPa, right? And we also know that S1 is equal to S2, which means that we know what S2 is equal to 7.1962. So knowing these two things, we can go to the chart. And when we go to this chart, we're going to have to find where this exists. So 0.1 and 719. So let's go back. Let's go find 0.1. 0.1 is 1 bar. Okay. I was making sure. So 1 bar right here. So if we slide across this, right, and we go right across, we need to pick up some numbers here. So is our value, how would we find any values for U here? Does our value fit inside of here, yes or no? Of the things we know about.
Yeah, it does. Below the maximum.
Yes. So what he said is that SF, S2, SG. Essentially what he said is that our entropy value is a little bit less than this, which means that it fits inside of here. It's somewhere in the middle here. We don't know where quite yet, which means we have to find what? quality, correct. So we're going to do that right now. So I need to hold on to these numbers, so I'm going to pull this over here to the side. So we would then say that x2 is equal to our value, which is I need to pull this down so I can read it, 7.1962 minus the S value, or the F value, so the one for saturated liquid, which is 1.326. So let's go back over here, 1.326. And then we divide by SG minus SF, which is 73594, so 7.3594 minus that same value, so 1.3026. So this right here is our number. Then I pull out my calculator that is not in the drawer that I want it to be in, and we do the things and the stuff. So we have 7.1962 minus 1.3026, and we divide by 7.3594 minus 1.3026. And we get an answer of 97% quality. That is a lot of quality. That's high quality stuff there, guys. Is that okay for thermo humor? So 97.3% quality. Okay? So now that we have that, we can then find the next part, which is we'll just do U2 would be equal to UF plus X2 times UFG, which is UG minus UF. And I will get us an answer to that very fast because we are running out of time. So let's do that. So we have times, let's do this, 2506.1, 2506.1 minus 417.36. And then you add the initial one, which is 417.36. And we get 2449 is our U2. So 2449.82. This is kilojoules per kilogram, okay? Well, there's still something else that we need. We need to find, oh no, we already know S2, never mind. It's because that was part of the case, we're S2. So, U2 is equal to this, right? Which means that we can then find what our initial state is, right? We can find our initial problem, which is, in the solution, we'll go down a little further here, and we'll write out that. So work is then equal to M times U1 minus U2. And since we know U1 and U2, you guys will probably be wondering, well, wait a minute, do we have this other thing? Like, how can we find mass? It's not here. Does anybody have an idea how we'll find mass? This will be a little fun. I'll start you off here, though. I'll put a parentheses here, which means that that's where we're going to insert that part. Tell me, what goes into this? Correct. So Tanner is right. Essentially what you can do here is that you can divide big volume by little v1. And what that does is that the big volume cancels with the other big volume consisted of specific volume, and then the mass goes to the top. So whatever this ratio is, you get the mass of state 1. Which, if it's the mass of state 1, it's the mass of state 2. Nothing left. So if you do this, you will get an answer for the work, and I will do that really fast just to be sure that we get something somewhat good. 0.04 divided by 0.2678. Okay, gotcha. Times U1 minus U2. And let's go where U1 is, which is 2826.1 minus 2449.82. And you get a final answer of 56 and some change, 56.2, and this would be in I assume this would be in kilowatts then, yeah, because we have kilojoules per kilogram over here times that. So I know this would be in kilojoules, not kilowatts. Kilowatts is per time. So kilojoules. So this would be our answer with that for that specific one, for that process where isentropic S1 is equal to S2. So now what that means though, before we're out of here, it essentially means that for this process, I'm just gonna draw something like, I'll draw this. How about that? We'll draw a little line here. So this right here is the high pressure line, or the high temperature line. This right here is the low one, right? So these lines are pressures. We're going to call this one pressure 1, which is the high pressure, and pressure 2 is here. Essentially, what this is that, although I drew this really poorly, so you're going to have to bear with me here. Essentially what happened is that we were up here as superheated at state 1, and we fell down in an isentropic way. No entropy change in the process. It was a perfect process, right? And we went to state 2 right here. And this makes sense kind of graphically because state 2 was in the saturated region and state 1 was superheated, right? And so now, as I tell you this before we leave, essentially what this means is that this right here is the line. That means that all other cases of the entropy, like, I chose the isentropic one where S1 is equal to S2. All other cases of how the process runs has to be this way, somewhere. Has to be over here somewhere, right? But there's a limit to how far it can be over there, obviously. What I'm saying is it has to be to the right of this because we cannot go back this way. Remember, entropy is only gained from a process, not lost. So we can only go towards the right. And this is a entropy and temperature diagram. So that is what I wanted to tell you. And like I said, this question, is kind of... I wish it would have just had like some numbers to get us to an answer besides choosing a case. But this is the one I could find that was sort of helpful. So... right here, very straightforward question, not a lot of twists and turns into it. And in your homework, which will be posted today, which is this right here, you will have some things like this. So for example, look at this. Hey, an air in a rigid tank with a paddle wheel. Look at that, although it's air, but you get the point. There's questions like it. So you guys got some things to do. And hopefully this helped just a little bit. And we'll get into control volumes because the last part of that homework is control volumes, and you will have to do that. And control volumes will be next time and probably a little bit of Friday, so you will know what you're doing before then. I'm going to go ahead and stop this and